Modern buildings comprise several areas containing valuable assets and agents. For example, here is a floor plan of a building comprising a corridor, a server room, and a Wi-Fi area. From the corridor, the Wi-Fi area is accessible. As is the server room, containing valuable equipment. Changes in this environment, arising from the movement of agents and assets, can lead to security breaches. For example, if a visiting technician wants to enter the server room to fix a printer, then if the access control policy allows it, she can do so. However, she can tamper unnoticed with the equipment since she already has access to the room. Our approach maintains an explicit representation of the environment's topology, such as the structure of the building, including assets and agents. We monitor unexpected topological changes in the environment and then perform speculative threat analysis to identify future violations of security requirements. During planning, we generate an adaptation strategy to prevent or mitigate such violations. Selected security controls are applied when necessary. Here is how the approach works in practice. Consider the security requirement for a visiting technician never to be in the server room unaccompanied. When she tries to access the server room, the system preemptively forbids her access. But after employee Bob enters the server room, her access can be granted. Let's see how this works. Here is the bi-graph model of the building, showing agents and assets contained in rooms. Bi-graphs enjoy well-defined semantics of dynamic behavior expressed as a set of reaction rules, which rewrite portions of the model and thus allow reasoning about possible future configurations that are reachable from the current one. Security requirements are represented as properties to be maintained throughout execution, such as a visitor being accompanied in the server room. After identifying violations by model checking, which correspond to counterexample sequences of actions, an adaptation strategy conditionally forbids or enforces certain actions. In this finite state machine, red states represent violations, and transitions to green states represent actions that the system can take to mitigate such violations. From an initial state, if the technician Mallory enters the room, a violation can occur because she will be in the room unaccompanied. Therefore, the system preemptively forbids access to Mallory or otherwise asks Bob to enter the room. Let's now consider a cyber-physical environment. Access to the Wi-Fi area allows mobile device connection to the network and allocation of virtual machines in the local cloudlet. For example, here Bob is communicating with a cloudlet through his mobile phone with an unencrypted communication link in order not to run down his battery. Communication with such virtual machines is risky. Someone nearby can eavesdrop on the information exchange. Again, this is how it works. Reaction rules now allow connection to the Wi-Fi, provisioning of virtual machines, and information exchange. A security requirement expressing confidentiality can state that a user's information token cannot end up in another user's phone. During an unencrypted information exchange, a user's info token may also end up with another user connected to the network. Again, here is the adaptation strategy. If Eve, another employee, accesses the Wi-Fi area and connects to the network, and Bob transmits information to a virtual machine, confidentiality is breached. Possible adaptation actions may be in both the physical and the cyber domains. For example, Eve could perhaps be forbidden from entering the Wi-Fi area or connecting to the network, or alternatively, the ability to perform unencrypted communications is revoked. Here is how this works. As Eve enters the Wi-Fi area, and connect to the network, encryption is enabled on Bob's phone as the least intrusive option.